Okay, so we have a couple of fun things today. So on the schedule, it says that today we're going to move on to chapter 12, which I am ready to do. We have slides that are posted before the lecture as well in the files part of Canvas. But I wanted to finish up a couple little things in chapter 9, and then we have a bunch of chapter 9 demos for you. And so, or 3 of them at least. So hopefully it'll be a bit more of a fun time today. So just to begin, I wanted to start off by showing you some capillary tubes. And I've been told that I can't get mercury anymore because apparently they don't like us just having open containers of it in lecture halls. But we do have colored water, which, you know, is honestly a great material for capillary tubes, like no joke, because it has a really high surface tension, right? Water has not only one of the highest surface tensions of liquids, but it also has a really small contact angle with glass, which means that not only does it have strong cohesive forces, the forces holding the water together, but it also has strong adhesive forces, the forces holding the water to the glass, which makes it climb up these capillary tubes. Okay, so I think we can see these tubes. So I'm going to dump water into this big reservoir. Can you see that? Filling the bottom. And then if we were just listening to Pascal, we would expect these to all be at the same height. But what you can see here, as we go from right to left, the diameter of these tubes is decreasing, getting to the point where the surface tension capillary tube effect is strong enough that the water on the left side, you can see, is significantly higher than the water over here on the right side. And so with the tools from this class, we could calculate that height. But as you can see, you know, unless your capillaries get down like near the cellular level, the effect is really small, right? The difference in height between the left and the right side here, it's steadily increasing. So this is the biggest tube, next biggest, or sorry, next smallest, small, and then smallest. So that height continuously increases. It's proportional to the inverse of the radius of the tube. So if we make the tube twice as small, it goes twice as high due to capillary action, sort of above the level that just the volume would tell it to travel through with Pascal's principle. But we would have to make a significantly taller tube to start to see this have really noticeable effects. And you can see how, you know, it's kind of a limited force in the sense that if you're a plant taller than a couple of meters, capillary action is not going to do much for you. So that's why you need that evaporative water loss on the top, pulling the strands of water through their internal cohesive forces on the bottom through this island. So anyways, capillary tubes. Now you've seen it, you know, this is the thing. Hopefully it feels more real. But anyways, so that's our first demo, just showing you that capillary tubes exist. The second one's a little bit more fun. So we've got a pump for air. So it's going to pull in air from the atmosphere and force it through this gray tube. And then this tube has a couple of different holes in it of different diameter. And so what we can do is you can turn on the air. And when we place the ball in the airstream, it stays there, which is really weird, right? So this is related to the last thing that we talked about yesterday, which is sort of Reynolds number and turbulence. Okay, so the ball is large enough that we have a Reynolds number. You know, you can calculate it, and maybe I'll make you do that at some point, but off the top of my head, I would guess around a few hundred to a couple thousand, so in that range. So we do end up getting wakes behind the ball. And so the result of these wakes is that they dissipate energy. Once you get turbulence, we can't use Bernoulli's law nicely. So these wakes dissipate energy, so the pressure above the ball is lower than the pressure below the ball, so the ball is pushed upward. Okay, so its weight is pulling it down, and this difference in pressure is pushing it upward, and they balance when the ball is at some specific height. Because, as the air flows out of this tube, it's not going to stay in a nice column, it's going to spread out. So at a certain height, those forces will be nicely balanced and able to levitate the ball. If you go too far away, it'll fall down. If you go too close, it'll be pushed back up. So it's kind of like a spring. It has some equilibrium position that the ball wants to return to in the vertical direction. But the really cool thing is it also has an equilibrium position in the horizontal direction. So just to show you this, if we balance it, if I push on it sideways, if I push too hard, it'll escape. But if I push on it sideways, it'll also return back to the middle. Okay. And this has to do with the fact that, again, here the air is free to the atmosphere. So the air in the center of this jet is going to be moving really fast. But as we get closer to this atmospheric air, it's moving slower and slower. And so we can think about the Bernoulli effect, right? We can think about the fact that when the air is moving faster in the middle, there's a lower pressure region. And so when the ball is pushed sideways out of the column, there's the fast air in the middle, which is lower pressure. And then there's the slow air on the side, which is higher pressure. It pushes it back into the column. So here's the column of air. We try to push the ball out, and the pressure differential in the horizontal direction also stabilizes it. So it's stable in every direction, which is why it'll just stay there. I'm going to turn this up. Okay, so this is kind of hard to see from very far away, but I wanted to demonstrate some of the dynamics here. So at this region, the pipe in the bottom, this lower pipe, is thick. Here, the pipe is thinner, and here it's thick again. Can you hear me okay over this? Okay, good. So Bernoulli's equation, it's misused a lot of the time, but in this situation, we can apply it in the closed section of the pipe. So the horizontal pipe, we can use the Bernoulli effect. And so this region of the pipe is wider. And so if we kind of ignore the compressibility of air, which does change things a little bit, but not too much, then the air flowing through this region has, let's say, some pressure, P. Then as it goes to a narrower region, from the continuity, its velocity is going to increase. More air has to flow through the pipe. As its velocity increases, the pressure in this region decreases. So this region has less pressure to push the ball, so the ball achieves a lower height. So this middle ball in the narrow section is at a lower height than this ball in the upper section. Now we return back to a section of the same diameter as before, and you can see the ball is pretty close to the same height, but a little bit lower. And this is due to turbulence in the pipe. So as the air flows through the pipe, especially the restriction, its Reynolds number is pretty high, a few thousand. And so what happens is that this turbulence steals some of the energy. It's like a form of friction. And so there's not as much energy by the time you get to the end of the pipe to apply a pressure differential. Okay, so I know it's hard to, I probably should have given the explanation with that off, but anyways, so lots of cool things, and you can do this at home. I'm sure you can find like a ping pong ball for beer pong or something somewhere, and you get a hair dryer. Preferably don't turn it on the heat setting because you can melt these. Hair dryers are pretty powerful, but if you turn it on like a cool blow setting, you can do this at home, and you can even kind of angle it, and as long as the airflow is high enough, it'll stay stable in that stream even if the air is coming at an angle. So I can try it. I'll try it here. So we've got it in the streams. Let it stabilize. And then we can kind of tilt it sideways. And it still manages, just to show you, still manages to levitate. There's nothing below it. So that's because the reason it's floating is due to these, right, these turbulent wakes, and that doesn't care about the fact that gravity is pulling at an angle. So there's a turbulent wake supporting it in this angle direction, and then there's the difference in fluid velocity supporting it in the perpendicular direction. It doesn't matter how you tilt those axes, it's stabilized in every direction. So that's why you can angle. But it's a really fun thing. You can do it at home with your hairdryer. You can have a little ping pong ball way out here and just keep it hovering. Okay, so for the next demonstration, I need some volunteers. That's how you know it's going to be a good demo. But okay, so here we have two metal, so a metal plate and then a metal container, basically. And so there's no glue or anything. This is an O-ring, just to prevent the air from being able to flow out or flow in, I could say. And so what we're going to do, so you can see I can easily take these two things apart because there's the same amount of air pressure inside as outside. But what we're going to do is we're going to evacuate the inside. So this is a vacuum pump, just like what's in your household vacuum cleaner. So we can pull the air out of the middle of this, except this is a lot stronger. So it can get almost down to the zero pressure, like pretty close. So there, remember, the atmospheric pressure can make mercury travel up 76 centimeters. This vacuum pump can make that, if you applied it to the surrounding pool of mercury, it would maybe travel up a millimeter. That's how strong vacuum is. So anyways, we're going to evacuate it. So now the only force that will be happening is because of the atmospheric pressure. And I'm going to ask two people to try to pull these apart. We'll see if they can do it. So anyways, so I'll connect this to the vacuum pump, turn on the pump, and yeah, okay. We'll let it pump down for a second, and then I should be able to completely disconnect this so you can be sure that there's no like weirdness happening, right? Just pump down to a pretty good level. Things are always super greasy because they have to be vacuumed. So anyways, this is things. So two volunteers who think they're strong enough to pull this apart, or if you want to try it by yourself. No volunteer? Yeah, come on down. Anybody else? You're coming too? Awesome. Thank you. Okay, so first you can try to pull apart yourself. How's that working? Not too well. Okay, so if you want to give your partner here at one handle, so don't hurt yourself and be sure there's nothing you're going to fall on if something would happen. But you can see it as hard as you can try, like it's, as hard as you can try, nothing. Isn't that crazy? So this isn't a very big area, right? This is only very similar to that suction cup in our example. Maybe, a round of applause for our volunteer. So, only what, 10 or 20 centimeters across. And so the pressure or the force being applied to these plates is that area pi r squared times the atmospheric pressure. But it turns out if you do the math here, this can take like 400 pounds of pulling force to separate. So if anyone could do it here, I would be pretty impressed. But what we can do is I'm going to set it down, we can open this valve, let the air back in. Now I can take it apart easily. Pretty cool. Okay. So anyways, so those are the demos I have for you today. Hopefully it makes some of these effects feel a little more real. And you could really do all these at home. I mean, building one of these little enclosures is a little hard, but if you just hook up your cleaning your vacuum cleaner hose to any sort of thing that separates into two parts that can reasonably hold air, you'll have the same thing happen. It's just that usually the seal will break at some point. And so the benefit of this type of specially made device is that it has a really beefy O-ring that's going to keep all the air out and let you see the full effect of atmospheric pressure. So it's really crazy. We live at the bottom of an ocean of air, and it's something we really take for granted a lot of the time, but it can have some very powerful effects. Okay, so we left off on Reynolds number. So just to remind you, Reynolds number is the balance of inertial forces relative to viscal forces. So it gives you a sense for how the fluid is going to flow either around an object or through something like a pipe. We have a sample calculation here for a salmon where we put in the speed of the salmon, 0.5 meters per second, the length scale of the salmon, so just roughly how big it is. And any problem I give you about Reynolds number, you won't have to be very precise, or it'll be obvious what the length scale is, like the width of an object or the diameter of a pipe or something like that. Those are all sort of length scales you might see. And then over the viscosity of, in this case, water, which remember is temperature dependent. So you, in theory, want to know the temperature of this. And that depending on what Reynolds number you find in a certain situation tells you what the friction drag force looks like. So I know that there are a lot of coefficients and things. You actually know all of these coefficients, I think, except for the C sub D, which is just, it's called the drag coefficient based on the shape of an object. But at the end of the day, what I really want you to know, and the takeaway from this, is that for a high Reynolds number, our drag force is like some number times v squared, where that c, that little c is like 1/2 big C rho A. I'm just condensing all that down into one coefficient. And if you need this sort of thing in a problem, I'll just give it to you in terms of this little c. So don't worry about the specifics. You can see that it's kind of nice when you dig into it. It depends on the area of the object, which makes sense. Like if you have a sailboat, you want a bigger sail because you want more drag to pull you forward. And it depends on the density of the fluid and then on the shape of the object. But then for a low Reynolds number, we have the drag force is just proportional to the velocity to the first power. So this is why a lot of classes skip over drag forces, or they'll just say, well, v squared, or well, v. It's because it really is dependent on the situation. And that's what the Reynolds number gives you the power to do, is to tell what situation am I in? Am I in a situation where drag goes like v squared, where if I go twice as fast, I have 4 times as much drag? Or is it just linear, where I go twice as fast, I have twice as much drag? So it's a big difference. It has a lot of important implications, which situation you're in. And it's really characterized by the Reynolds numbers in this picture. So I'm debating this, but I think if I end up giving you a Reynolds number question on the final, I'll probably give you these ranges because I don't want you to have to memorize Reynolds number ranges. That's kind of annoying. But you should just know that for a pipe, if you have a few thousand Reynolds number, that's where you're looking at turbulent flow. And then for an object like these ping pong balls in a stream, when you have, again, a Reynolds number of around 1,000, that's where you're getting turbulent flow behind the object, which for our little ping pong balls was able to stabilize them. Okay, and so like you can see for these high Reynolds number cases where we have turbulence, that's where we have a drag force proportional to v squared. And that's because when you have turbulence, the energy is dissipated more easily. There's like more friction happening with turbulence because the particles are really bouncing into each other, taking all these random paths, twirling and making vortices and stuff. Whereas for laminar flow, which is on the left here, which is for low Reynolds number, in that situation, friction isn't as bad. That's why it's just proportional to velocity to the first power. Okay, so these are the important things from like the last 5 minutes of last class. Are there any questions about these principles. How Reynolds number determines what type of drag force we have. And then, you might be given a question where you have to draw a free body diagram and, do some of the stuff from 3A, but just with these new types of forces. Okay. So like I almost got to get into this yesterday, but so it turns out that Reynolds number and viscous fluid flow is really important for measuring blood pressure, or at least the way that people used to measure blood pressure, and that it's still like the most accurate way, commonly used, most accurate non-invasive way. Because you can always just open someone up and put a pressure sensor in their artery, but that's not very fun. So what doctors and scientists came up with was to have this blood pressure cuff, which is basically a tourniquet. So it cuts off all of the blood flow into your arm, which is kind of weird when you think about it, that this is like a regular thing people do. But if you take a combat-oriented first aid course, you'll learn that you can actually leave on a tourniquet for like 5-6 hours without any negative side effects. So if someone is severely bleeding from an arm or a leg, please, please, please put a tourniquet around their arm and potentially save their life. But you have to really winch down on whatever you use because it's hard to stop all of that blood pressure. But anyways, so we stop the blood flow through the arm and we listen with the stethoscope and we hear no flow. We hear nothing. But as we release the pressure, release, eventually the fluid starts flowing. But because of all this pressure, the openings, the artery size is very small. And if we go back to Reynolds number, you can see that the smaller, so when these, let me think about how to frame this. So, okay, when we have these small openings, we end up getting hold on, this feels backwards. I might have to think about this some more. But anyways, the small openings with the high fluid flow rate, that's it. There's a nonlinear relationship. So, okay, as we decrease the openings, we increase the velocity of the blood such that the inertial forces are greater than the viscous forces, and we get a high Reynolds number and turbulent flow. And so what that means physically is that when you listen with your stethoscope, you hear like a whooshing sound, like you hear the blood flowing into the arm through these constricted passageways. And as you release, so that first point where you start to hear that noise, that's your systolic pressure, the high pressure in the pumping cycle. And then you keep listening, you keep hearing this whooshing noise until eventually you release the pressure enough that the arteries have opened fully. And at that point, the pressure you're reading is the diastolic pressure, and you stop hearing this whooshing sound because now the flow is laminar, it's unobstructed. Okay. And the really nice thing here is that the velocity, because it's viscous flow, is highly dependent on radius, as we talked about yesterday. That like Puiseux's equation, that the flow rate is proportional to radius to the 4th power. So the velocity is proportional to radius squared. So that's why even when you have these small constrictions, the velocity of the blood starts to really, dramatically change. And as a result, we get into high Reynolds number, where velocity is in the numerator really quickly. And even though we're changing the length scale, which is something I always get momentarily confused by, the velocity is changing faster. So even though the length scale is being shrunk when we constrict an artery, we have a velocity that's like the square of that. So overall, we get an increase in the Reynolds number. We get turbulent flow, like in this pipe picture on the top right, and we get the little whooshing sound. Okay. So if you do the heart group project, you'll learn more about this and some of the other methods that people use for blood pressure measurement. Okay, so then we have an example for you So we have a viscous fluid flowing through the pipe shown. The 3 marked sections are of equal length. Across which segment is the pressure gradient the largest? And so this is something that I didn't get into much yesterday in lecture, and then also misspoke in office hours. So sorry to the people that were in office hours. But so when we find this pressure gradient, this is a pressure gradient along the length of the pipe when we're talking about Poiseuille's equation. Okay, so this delta P, which is due to the drag force, is basically communicating the fact that to get fluid that's thick, that's viscous, including water, to some extent, to flow down a pipe, we have to have a higher pressure from where we're pumping and a lower pressure where it's going. In an ideal fluid, the pressure would be the same all along that length of pipe, and that would be enough to move the fluid through it. But because you're losing energy to friction, the flow through the pipe requires a pressure change, a pressure gradient from high to low in order for the fluid to flow. And so in this problem, what they're asking you to compare is how does the pressure change across A, across B, and across C? And so what we can do is we can go back to this pressure drop equation, and we can see that the numerator is based on the viscosity of the fluid, eta, the speed of the fluid, v, the length of the pipe, L, and the denominator is based on the radius of the pipe squared. And so in our example, the only thing that's changing is the radius of the pipe. The lengths are the same, fluid's the same, speeds. The speeds, will change, but the radius is 1 over r squared is by far the strongest effect. So say that's proportional. Delta P is proportional to 1 over r squared. And so as we get into the bigger section, section B, the denominator increases, so the pressure change decreases. So the pressure drop here is the smallest, but they want to know what pressure drop is the largest. Okay, and so what we have to think about is the fact that as the fluid flows through this system, we still have the continuity equation. We still have A times V is conserved. And so, oh, actually, sorry, I see what's happening. So this is the smallest radius. This is the biggest, and this is actually a medium amount. Okay, so then this would be the largest delta P. This is comparing delta P's. So, this sounds technical, but the moral of the story is that if you try to force a viscous fluid through a smaller pipe, you have to apply more pressure for that motion to occur, which hopefully feels reasonable. If you're imagine trying to squeeze honey out of a honey bottle. If you take the lid off of the honey bottle, very easy. If you put the lid on and it just has that little small nozzle opening, it's significantly harder. You have to maybe squeeze on the bottle in order to get that flow started. And that's because you're losing energy, you're losing pressure as a viscous fluid flows through a pipe. And that's highly dependent on the radius. Okay. And so we're going to quickly end with this, but like I said, if you do the HEART project, you'll get to learn a lot more about this stuff. So we can map blood pressure. So you can see here measured in millimeters of mercury. So remember that 1 atmosphere is like 760 millimeters of mercury. So that's just telling you that if you want to build a mercury barometer, it needs to be about 2 feet tall, or 3 feet if you want to be comfortable without any mercury spilling. And so human blood pressure, this is a gauge pressure. So that's in addition to the atmospheric pressure. Our blood has, you can see like 15% more pressure than 1 atmosphere, something like that. But as you can tell, it's something that changes over time because the heart is a really complex pumping apparatus. And so when the heart is pushing, we get to this systolic pressure, which is the high point. So that's where we first had blood flowing when we were trying to measure it. And then as the heart goes through its pumping cycle, at different stages, it's pushing less fluid because it's sort of, you can imagine it as resetting. It has to pull fluid in, close valves before it can open them and push it out. And so that's where you get this base pressure or diastolic pressure. And I just wanted to show a picture of the heart here. You know, it's a really nice multi-stage pump, and a lot of human pumps are similar to it, actually. And I wish we had more time and could get into some of the details. But anyways, so I wanted to give another sample problem with viscous fluid flow. And so this one is specific to the circulatory system. So we have a woman lying down, and her arm is horizontal. So we can imagine there's a horizontal pipe. And one of the arteries that we're considering has a length of 20 centimeters, so 0.2 meters, with a diameter of 4 millimeters. So we could just say with a radius of 2 times 10 to the minus 3 meters, just to convert as we go. And that the average speed of the blood through this artery, which is something that you can measure with a few different approaches. So one of which would be using the Doppler effect with something like ultrasound, which we'll talk more about later, is 9 centimeters per second. So we could say 0.09 meters per second. Okay, and we want to know what's the pressure drop, delta P. And so we just were looking at the pressure drop equation a minute ago. It's on a previous slide. So just to write that down for you, it's 8 eta VL over R squared. And so we know most of these numbers. We know the 8. So eta in an exam, you would be given it. But if it's a homework problem, once we get the homework working, then you'll have to look in the tables within the text of the electronic book that's included with the homework. So for blood at a normal body temperature, it's about 3.5 times 10 to the minus 3, and that's units of pressure times time. The velocity is 0.09 meters per second, and the length is 0.2 meters. And then we divide by the radius, 2 times 10 to the minus 3 meters squared. And let's see, if I calculate this really quick. So we have minus 3, minus 2, minus 1, or minus 6. So we get something times 10 around, yeah, perfect. So 126 pascals, which is a pretty small pressure. I mean, so if you convert that to millimeters of mercury, remember that there are 100,000 pascals in an atmosphere, and that's 760 millimeters of mercury. Then we get 0.95 millimeters of mercury. So, even though millimeters of mercury aren't a real metric unit of pressure, they're often present in blood pressure measuring devices and in other laboratory equipment. So it's convenient to know how to do that conversion. Since it's not technically a metric unit, I would give you this conversion on an exam if you're worried about memorizing it. But it is good to have somewhere in your mind that mercury goes up, about 0.767 meter in a barometer. But anyway, so this is a good thing. This should feel like it checks out, because if our blood pressure is in the region of hundreds to 80 for a normal healthy person, then losing less than 1 millimeter of mercury of pressure along some pretty long stretch of artery is not too bad. It's telling you that by the time you get down to capillaries, maybe we'll have lost the majority of the pressure of our blood flow, but then we can rely on capillary action to take over and cause the blood to move. And then once it's in the veins, it'll have some small pressure that's enough to pull it. Mostly, well, anyways, which you can read more about if you decide to do the heart project yet again. Okay, so any questions about this problem? Good. So I just wanted to add a fun example here really quickly to show how clever nature is, which is that, obviously for giraffes, they have to pump fluid up some vertical distance. And remember that, so since this is a column of blood in an artery, that we can use rho GH as sort of the change in pressure due to gravity. So even without viscous fluid effects, we're going to have some higher pressure at the heart than we would have at the head of the giraffe, just due to the fact that you're trying to push the fluid up the neck. And so it turns out giraffe hearts, unsurprisingly, are very strong pumps, and they have significantly higher blood pressure than humans in order to have enough blood reach the brain. But the cool thing is that in giraffes, when they bend their head down to drink, you have the opposite problem now, right? Now the heart is applying way too much pressure because this delta P is rho GH is now pushing the blood. So it has a higher pressure at the brain than at the heart. And so giraffes have a lot of clever mechanisms to help prevent this, which includes restriction. So they can, humans can do this as well. Like when you start running, your arteries open up, they dilate to get more blood to the muscles that are being used. But giraffes have this to an extreme level. When you're talking about the arteries in their neck, they can dilate them and constrict them to a much larger extent than humans. And because of these viscous flow equations and the high R dependence of fluid flow through some pipe, you can balance this huge change in pressure due to rho GH, that weight of the fluid above or below you. So just kind of a cool example tying things together. And then I just wanted to grab this picture from the book where you can really see what's happening with the blood as it flows through the body. So you can see that, if you convert blood pressure into pascals, that a systolic, high pressure is around 12 kilopascals. And that, when the blood is flowing through the aorta and the major arteries, the fluid drop is very minimal. And that's because blood, again, it's a viscous fluid, so it's flowing through these large openings. And so since the radius is large, that the pressure drop, delta P, is small, right? Delta P, just to remind you, delta P goes like 1 over R squared. But then once we get down to these minor arteries and then into the capillaries, the pressure very quickly drops off. So this is the effect where, due to that R squared dependence of delta P, the smaller the pipes get, very, very rapidly, the fluid flow rate changes and the pressure gradient changes. Okay. But as you can see, the body can handle this because while there's only one aorta, there are billions of capillaries. So the blood is just split into all different directions. And due to capillary action, you don't need very much pressure in order to continuously move blood through these small pipes. And then once we get into the veins, you can see the pressure is almost dropped to 0. So blood flow through the veins is very precarious, but that's why veins have special mechanisms that are basically like one-way valves that help prevent backflow. So blood can only, for the most part, flow one direction in veins. And then there are a few other cool techniques the body uses that, again, you can look into in your project. Okay, I'm going to skip this problem just because it's quite long and I want to move on here. Uh-oh. There we go. And so now we can move on to this, but first let's take a break. So a few minute break and we'll move on to the next chapter, which is thermodynamics. So pretty big change of pace. Anyway. I don't know. While we're on break, does nobody else want to try pulling these guys apart? It's pretty fun. You know? If you change your mind, I'm done. Oh, excellent. Okay. Timely announcement. I just found out that Canvas, the Pearson homework has been resolved. We got to the highest level of Pearson tech support and they pulled through for us. So sometime later today, I will make an announcement with more details. There's still no homework one though, right? No homework one. Yeah. Yeah. Yeah, but there is a quiz today, and your discussion section leader will remind you of that, but just don't forget. Yeah. The quiz is one scenario, but a couple of different questions, or a few different questions about that scenario. And so it uses some ideas from surface tension, some ideas from hydrostatic pressure, a few different concepts. So it's a realistic example that you can do at home if you so choose. Anyways, that's a very good question though. Yeah. That's a good question. I like that idea. I'll think about it. Because I do want you to have some chance to do a lot of these fluid problems, since I think it's good to try them out and then get feedback on if they're right or not. So I like this. I'll definitely ask you some fluid questions in homework 2, just to give you some sort of credit for learning this stuff. Obviously the final is another place where that's true. Yeah. No fluids in motion on the quiz, but that's a great question. So the quiz is about static situations, equilibrium situations. Yeah. So, but I do want you to learn fluids in motion, and your TAs are going to go over them more with you today, because it will be potentially on the final. Okay, so I know probably never long enough of a break, but I think we should go ahead and get started. So as you can see, this is going to be our topic for the next few lectures. And even after those, chapters 13 and 14 are still related to thermodynamics, just on sort of more advanced topics that we're kind of mostly skip over, to be honest. But we're going to have a lecture, one lecture on chapter 13, which is going to be about kinetic theory, so like how fast molecules are moving when they're heated up, and then one lecture on chapter 14, which is about entropy and that sort of thing. So we'll have to go quickly through those sections, but I'm going to tell you very clearly what I'll expect you to know, and it won't be everything in the book on those two. But on chapter 12, it is basically all of the fundamentals of thermodynamics, and so I really do want you to know just about everything in chapter 12. And so that's what we're going to dig into here. So I just really want to highlight that the ideas behind thermodynamics are really the origin of the Industrial Revolution, and therefore the entire modern world that we live in. So it's really hard to undersell how big of a change steam engines made in the world, and we're going to seek to understand them as part of this course. But we can also understand their modern predecessors, so internal combustion engines and turbine-based power plants, all sorts of things like that. But anyways, I just wanted to highlight this. There's really no other invention, computers maybe, but I think steam engines change the human experience more dramatically than anything else. And in order to develop efficient and powerful steam engines took the continuous and sustained effort of physicists developing thermodynamics at the same time. So like as people were trying to build these new steam engines, there were physicists trying to understand how they work and predict how to make better ones. And so all of this stuff is related to that. The first thing we're going to talk about is heat, which is different from temperature, even though the way that we use heat every day, colloquially, is basically to mean temperature. When I say that it's hot outside, I just mean that the temperature of the air is high relative to normal. But heat in physics is the idea of transmitting energy, so either giving energy or losing energy via these thermal processes. So before we get into that, it's worth mentioning that temperature is really just kinetic energy. Okay, so when an object, if I take this bottle of hand sanitizer and I'm moving it along a line, it has some kinetic energy, 1/2 mv squared, and it's very easy to calculate because the whole bottle is moving in the same direction. But when I have a box full of gas, since that's the most dramatic example, the whole box of gas can be stationary. So the box isn't moving. On a whole, on average, the gas isn't moving. But each little particle is moving really fast. So every little particle of gas has some kinetic energy, 1/2 mv squared. And if you add all of those up, then you get the thermal energy of the system, which tells you its temperature. And we're going to talk about how to do both parts of that. So in chapter 12, we're going to learn how to go from energy to temperature. And then in chapter 13, we're going to talk about how to actually get the velocities of those gas molecules, which is often important. For example, when designing vacuum pumps, you need to think about the velocity of these gas molecules. But anyways, so for gases, when you heat them up, the particles are just bouncing off of each other faster. For liquids and solids, as you heat them up, you're still imparting kinetic energy, but it's more of a vibrational kinetic energy. Okay, so the particles, the molecules aren't moving very far, but they're kind of oscillating back and forth. And in those oscillations, they have kinetic energy. As they're moving right and left, they have 1/2 mv squared. And so as they turn around, they lose that kinetic energy, but they're giving it to their neighbor. So there's always, if some particles have kinetic energy, some don't, maybe they trade it back and forth amongst themselves, but for an object at some constant temperature, the total amount of kinetic energy will be constant between all those microscopic particles. Okay, so in thermodynamics, there's this really weird interplay. So sometimes we think about these molecules and how they're behaving, how fast they're traveling, what they're up to. And other times we're interested in what we call sort of macroscopic variables. So things that describe the whole object, like temperature or volume or pressure. So it turns out, this was the brilliance of 19th century physicists, that these two things are directly related to each other. And I'm going to try to highlight that as we go through the course, even though the book doesn't really talk about it much. But, you know, like I was just mentioning, one example is that the temperature, which is a property of large objects, so this bottle of hand sanitizer has a temperature, is due to the motion of the small objects, the fact that they have kinetic energy. Similarly, the pressure in a balloon is a big scale property. Where does it come from? It comes from bouncing off, the change in momentum of these small particles, these gas particles, or the weight of water particles under gravity. So any big scale property of an object, remember, is always due to the small scale properties. And so sometimes you'll hear people use the word macroscopic for things like temperature and volume and pressure, and microscopic for things like the velocity of molecules or their change in momentum, things like that. So this is a really important idea. And when we get to entropy, this will be critical to understand, because without understanding the molecules, entropy just seems like magic. And this took so long for physicists to understand what the heck is happening with entropy. But we now know what it is, and we'll learn about it in next week, I think. But anyways, so temperature, we've got a nice picture of someone making liquid nitrogen ice cream on the right, which is a really fun pastime, would recommend. But what I wanted to talk about here is temperature scales. So we're probably all familiar with Fahrenheit and Celsius. They're the two most common temperature scales used for measuring everyday, like weather type temperatures and body temperatures. And so something that you can do with a gas, like you can see in this diagram, is that you can have gas in a container. And because of the ideal gas law, if we make the volume of that container not change, so we build it out of iron or something that doesn't expand and contract much, and we fill it with gas, and we surround it by this blue fluid with a temperature T, then we can measure the pressure of the gas, and that tells us the temperature. So you can make a weird, impractical thermometer based on the pressure of a gas, because think about the ideal gas law, PV equals nRT. If we keep this volume fixed, then as we increase temperature, pressure has to increase as well. So what we can imagine, so also what actually happens if you keep decreasing the temperature of a gas is eventually it liquefies. So liquid nitrogen makes up 70% of the air in the atmosphere-ish. And so liquid nitrogen is the main thing you get if you do this experiment with air and just keep cooling it down. Eventually you'll get liquid nitrogen. And so at that point, the ideal gas law stops applying. But what you can imagine is if you took this line that you get from actual experiment and you extended it down until you got to zero pressure, you can ask yourself, what temperature would that happen at? And it turns out no matter what gas or volume of container that you do this with, all of these lines come to meet at the same point. And so this was the first clue to early physicists that there was some minimum temperature we now call absolute zero. And so if you're using Celsius, that's negative 273 Celsius. And at that temperature, there's no longer any pressure in a gas. And so what that tells you is that there's no molecular motion. The molecules have to be perfectly still in order for something to be at absolute zero. And the fun thing is it turns out for a lot of complicated reasons, that's impossible. So not just hard, but impossible. Sometimes that's called zeroth law of thermodynamics, is that you can never actually get to absolute zero. So there are physics labs on campus that get to like within millionths of a degree of absolute zero. And that's really useful for a lot of studies of atomic physics, but you can never actually get there. So anyway, so that's where the idea comes from, and how, even with a simple apparatus, you can actually predict what temperature absolute zero would occur at, even if you can't get anywhere near it. So these are, these actual measured parts of the gas curve are all around, human scale temperatures. Okay. So we should talk about the 3 temperature scales. So first of all, try not to use Fahrenheit, if you don't have to. Celsius, you're gonna encounter a lot in problems and in the real world, just because it's the most common measurement scale for like metric users that are trying to measure normal temperatures, like body temperatures or room temperatures or something like that. And the conversion between Fahrenheit and Celsius is multiplicative and additive, which makes the temperature scales really annoying. Okay, so notably, instead of them just being all shifted somehow, Fahrenheit and Celsius are equal at -40 degrees, and then diverge more and more the farther you go from there in either direction. And so you probably learned how to convert these in like, middle school at some point. I won't expect you to really do that here, but what I do expect you to know is that to go from Celsius to Kelvin, we just add 273. And so Celsius and Kelvin, because they're just related by some additive constant, differences in temperature are the same in Celsius and Kelvin. So here we're increasing water from 20 degrees Celsius to 30 degrees Celsius. So that would be a 10 Kelvin temperature change. Okay, so I tell you this now so that you'll be prepared later, that basically anytime we have a delta T in a formula or some analysis, we don't have to care whether it's in Celsius or Kelvin. Okay, delta T, Celsius or Kelvin works the same way. But anytime you have a T, you need to get that temperature in Kelvin first. So the ideal gas law is probably something you all have worked with in chemistry classes. It only works if you convert the temperatures into Kelvin before you start plugging things in. Okay. So if you're ever in doubt, just convert to Kelvin. It's the real natural SI unit of temperature. And that's why Kelvin, we don't say degrees Kelvin, because a degree, that word in physics unit speak, is telling you that something's not really a unit, that we're referring to like some fraction of something. So for example, in angles, 360 degrees is the entire fraction of a circle. And in temperature, 100 degrees Celsius is the entire fraction up to the temperature of water boiling, something like that, right? And so anyways, use Kelvin is the moral of this slide if you're in doubt, but for delta T's, you can use either because they're the same. Any questions about this? Sorry if this is basic, but I think it's really good to get on the same page in regard to temperature scales, because you will just get lots of problems wrong if you try to plug in Celsius for T's in formulas. Okay, so like I said earlier, temperature and heat are not the same thing. So heat, which is represented by the letter Q, which I know we just used for fluid flow, but different branches of physics don't care what the other branches use their variables for, so we get a lot of confusion. So Q is heat, and it's really just a form of energy. So it has units of joules, just like any other energy would, or sometimes, like for food, we'll talk about energy in terms of calories. So if you read on the back of your candy bar how many calories are in it, you could convert that to joules. That's an amount of energy. And your body will use that energy to do work and to create heat. because you have to stay warm in order for your chemical reactions to work properly. And so the energy from the food, the chemical energy, gets turned into work whenever I move my arms or legs or something, and into heat, which is sort of the other place that energy can go in a system. And so we have to be careful with the sign of heat, plus or minus sign of heat. So generally speaking, positive heat is telling you that energy is flowing into a system, whereas negative heat is saying that energy is flowing out of a system. And so heat will flow based on a difference in temperature. So in order for my body to lose energy due to heat loss, so for the heat to be flowing out of my body, which is a negative Q, in order for that to occur, my body has to be at a higher temperature than the surroundings, which is true, right? Human bodies are, usually 10 degrees Celsius higher than their surroundings. And so we exhibit a negative Q, a negative heat flow. So energy leaves our body in thermal form. And so there's a nice example here on the left that there's this weird correspondence between heat and work. So on the leftmost picture, we have a flame, which is providing heat to this pot, and that's going to increase the temperature of the pot. But alternatively, we could do work on the water. We could rotate it with some paddle. And that work can also increase the temperature of the pot due to friction, basically, right? Like, you can rub your hands together, your hands are doing work, but the friction between your hands is turning that work into heat, which is changing the temperature. So what we want to make of this idea is what's known as the first law of thermodynamics, which is that the change in energy of a system can come from one of two places. It can come from work, which is like pushing or pulling, compressing, all these sorts of things, motion. Or it can come from heat, which is, like fire or, some chemical reaction oftentimes is the cause of heat, but it could also be like the electrical resistivity in a wire, like your blow dryer uses or something. And so the signs of this equation are really important. So this is delta E equals W plus Q. So this is work on the system, and this is Q into the system. Okay, so if I have this bottle of hand sanitizer and I want to give it energy, I can throw it, which is doing work on it. Okay, so that's giving it 1/2 mv squared kinetic energy. Or I can, blow on it with hot air, anyways, can blow on it, and that's giving heat, Q energy, into the bottle, because I'm providing a higher temperature region, and that allows energy to flow through these molecular collisions into the sort of molecular vibrations of the hand sanitizer bottle. Okay, so luckily, the way people have historically defined it, it just is all these things are positive in the equation for the first law. So it's not too bad to remember. There are no negative signs naturally in it, but just remember that this is energy, being input into the system. That's going to cause the system to have more energy. So I know it sounds easy now, but when we start to get into problems, it'll feel more complicated. Anyways, so just to get your mind thinking about heat, this question is, which of the following processes involve heat? So the brakes in your car get hot when you stop. Does that involve heat? Yeah, no. So well, it depends on what part of this process you're talking about, to be fair. But the fact that they get hot when you stop, that's due to work. Okay, so we're exerting some friction force over a distance d. And so that is able to change the temperature of the system, make it hotter. So a test tube held over a flame, that would be heat, right? We're creating a higher temperature environment in the flame, and energy flows from that higher temperature environment into the test tube, which is heating it up. So you place a bowl of water in the freezer. So is this heat or work? So this would be heat, but it's heat flowing out of the object into the freezer. Okay, so an important idea, once you understand the fact that that temperature is just due to molecular motion, is that heat is something that exists, but there's no like opposite to heat. So the thing that's flowing is the energy from hot to cold. There's nothing flowing from cold to hot. Okay, it's a one-way energy transfer. So the bowl of water in the freezer, energy is going from the bowl to the freezer because it's held at a lower temperature. But that is a heat-related process. So you quickly push a piston into a cylinder of gas, increasing the temperature of the gas. Is that work or heat? Good. That's work. So we've exerted a force over a distance. That's what we say in 3A. And this is actually really cool. You can make a fire starting device with this that some people, like survival people, like to have, which is literally just a small piston, and you just push on it real hard, and you put like some cotton ball or something in the end, and it'll light it on fire because you have done so much work in this very small environment that you generate enough heat that you can initiate the combustion reactions in the substance. So you're converting their sugars or whatnot into carbon, and start this chemical process. So they're called like fire pistons or something if you want to get one. Anyways, you place a cylinder of gas in hot water, the gas expands, causing a piston to rise and lift a weight. The temperature of the gas does not change. So you can see we can start to make these problems more complex very quickly. So when you place a cylinder of gas in hot water, that is heat, right? That's a positive cue. You're giving heat to the system. But then what does that system do? Well, instead of increasing its energy, so I should say this energy is related to the temperature. So instead of increasing its energy, it just immediately is like, nope, I don't want this energy, and it gives it away as work. So that's something that can happen because these three things just have to balance. There's no requirement that when you heat up an object that it changes its temperature. Alternatively, you can heat up an object, the temperature stays the same, but the object does some work. And oftentimes, the reality will be a combination of these effects. So you'll increase one of these things, you do work on a system, and maybe that increases the temperature and also causes heat to flow to the environment or something like that. So usually all three are interconnected. It's not just one to the other. Okay. Any questions about, this is the first law of thermodynamics. As we heard, the 0th law is like, you can't get to absolute zero. Hence the 0th law. But first law, very important. It's basically just a statement of energy conservation. We've just now split what we mean by energy into two different forms, work and heat. Okay, so the next topic then is what happens to substances when you heat them up, specifically solid substances and liquid substances. Okay, so solid substances have this really weird property where when you heat them up, they tend to expand. Not everything, but most things do this. And you can see that especially for metals, this is a pretty pronounced effect. Those are most of the examples given here. And so one place that you'll note, once you have learned about this, which I guess is right now, you'll start to notice it everywhere in engineering. So any large piece of steel, for example, so any large steel beam, you'll have to put some gap around it when you build it into a structure, because as the temperature outside changes from the winter to the summer back and forth, that steel is going to expand and contract. And as we'll see when we dig into this formula, the longer that beam of steel is, the more change in length will occur. So the more it can expand or contract. So when you start getting to the scale of like a bridge, all bridges over a certain size are built with little gaps in the road and underneath in the supports, so that when this thermal expansion takes place, it has a space to go into. It doesn't just break things as it expands, because this thermal expansion can apply an incredibly large force. If there's nowhere for it to go, if it's just pushing against something, it can easily damage the surrounding structure. So incredibly important for engineering, especially for larger objects like bridges and buildings and things. It's also something that's present in your house though, and that's due to what's called a bimetallic strip. So a bimetallic strip is exactly what it sounds like. It's a strip, so like a little small piece, small foil of two metals. So, you know, let's say brass and steel, or what are the, let's say aluminum and stainless steel, right? So here's aluminum, here's stainless steel, and we've welded them together, glued them together somehow. So what happens when we heat this bimetallic strip up? So, you know, obviously it's going to expand, but I guess I should describe the formula first, the way this works. So sort of the percent change in length, right? The fractional change in length is proportional to the change in temperature by some proportionality constant alpha. So if I double the temperature, if I have a change in T, delta T of some amount, then I'm going to change my fractional length. If I change that temperature twice as much, then I'll change my fractional length growth twice as much. So it's linearly proportional, but different materials will have their length change more or less quickly. So when we get this bimetallic strip, let's say that that this side is the aluminum and this side is the stainless steel, you can see that aluminum has a larger alpha than stainless steel. So what happens is this strip is going to curve. Let me just draw it again. Or yes, aluminum has the larger one. Let me stop second guessing myself. So that if you're running on a track, you'll know that the outer curve is a longer distance than the inner curve. And so the material that has the larger expansion rate, the larger alpha, will have will be on the outside of the curve. And so these bimetallic strips are a really handy way to physically do work when the temperature changes by a certain amount. And so this is the original way that thermostats work. So, you know, the little, I don't know where it is in this room, but the little boxes that sit in rooms, and you tell them what temperature you want the room to be at, they can have a little bimetallic switch or a bimetallic strip. And then you put a button over here. And when the temperature changes by a certain amount, the switch will just hit that little button. Or you can have it, you know, connect a circuit, or, you know, there are lots of ways, but they all just rely on this little motion in order to activate some mechanism. And so just with the power of thermal expansion, by picking the right materials and the right length, we can control how much they're going to expand, and for a strip, a bimetallic strip, how much they're going to curve in order to make that expansion happen. Okay. Any questions on thermal expansion? So we'll do a problem. So a cryogenic storage unit keeps tissue samples frozen at the temperature of liquid nitrogen, which in Celsius is -196. That's like the boiling point of liquid nitrogen. Suppose a 55 centimeter tall stainless steel storage rack is lowered into the liquid. How much does it contract from room temperature length? So we've got this storage, like some box basically, and it has a height of a little over 0.5 meters. And it's going from room temperature, 20 degrees Celsius, into this liquid nitrogen freezer, -196 degrees Celsius. And so you can see how, like, let's say in this freezer, you needed to hold that rack steady for some reason. You would have to like screw it, bolt it down. You need to understand how much is this going to contract. And so this is one of those situations where it's really useful to have an actual formula that lets us calculate that. And so what we can do is we can remember that our thermal expansion formula is that the fractional change in length is alpha times delta T. And so they want to know by how much does it contract. So that's just delta L. And then we're talking about a delta T. So is it important that we can convert to Kelvin, or can we just leave it as Celsius? Good, good. I see some nodding, some head shaking. So we can just leave these temperatures as in terms of Celsius, because the temperature difference between degrees Celsius is the same as between units and Kelvin. Okay, so we have to grab our alpha for stainless steel, 1.7 times 10 to the negative 5. And then our temperature difference is going to be, remember, delta of some quantity is a final minus our initial. So it's negative 196 minus 20. So this is negative 216. That's our delta T. And our length was 0.55 meters. And so now we can calculate our delta L. Just pull this up really quickly. And we get minus 2 millimeters roughly. 2 times 10 to the minus 3. And so for, you know, a half meter rack is pretty big, like this tall, you know. But even with this dramatic temperature change, because the overall length is not super big, you know, relative to like a bridge or something, the actual contraction is relatively small. But we could ask ourselves, what would happen if you put a bridge? So let's say you had a 50-meter long bridge. Now you're changing, you know, by 2 orders of magnitude. So this goes from 2 millimeters to 200 millimeters, which is, you know, 20 centimeters. So a pretty sizable difference. And it turns out that by the time you're at that scale, even summer to winter changes in temperature are enough to mess up, like, you know, where your bolt hole is located or something like that. But anyway, so this is where I'll leave it for today, since we're almost out of time. But hopefully it was a more fun lecture with the demos.